So the first part actually is easier. The second part is conservation of momentum, which is obviously another important topic, just like you learned in general physics. You learn about conservation of energy, and then conservation of momentum, and then conservation of angular momentum, and so forth. And so this part, Jackson, going back to a microscopic equation, and so that little string, because it suddenly changed back to so from macroscopic to microscopic. There's a question back of chapter 6, question 6.9, that asks you to divide the conservation of momentum. And I think also on momentum using the macroscopic equation. So that actually is very similar. So, and then the next question, 6.10, is conservation of angular momentum. And those are assuming you work it out. So, but sometimes it's needed. So I work out the solution for this question, these two questions. And when I post the homework set, I will include these two solutions in Canvas, so you can look at that. Especially one formula for the conservation angular momentum that you need to look at those questions. And then let's start the derivation for the conservation of momentum. Now, the starting point is just the same. You consider the particle first, but now you consider the momentum of the particle. So instead of the change of energy of the particle, you talk about the change of momentum of the particle. It's a bit difficult to do this. Maybe the other one would be better. Maybe it's a chart. It's a different kind of chart. Well, so we start with the change of momentum, and we call it mechanical momentum. Now, momentum is a vector, obviously. This is the momentum change, and now you work on the certain charge density and current density. So you have a certain volume with rho and J, right? So change of momentum is the force. So so basically, the right-hand side should be Lorentz force law, and this is the for continuum. So you have a charge density. So charge density basically you integrate that with the volume. Will become charged. So the force is charge times electric field. So you have rho E, right? And then you have the V cos B term. Now V cos B becomes a J cos B, because now with J you integrate that over volume, becomes a charge times the velocity, right? So on microscopically, it's charge times velocity and integrating a sum over that. So this becomes J cos integrating over volume. Okay. So, yeah, the chalk is this. the chalk I got from there is different color chalk. Look. And now you follow the same thing using the now this is the microscopic Maxwell equation. So Ampere's law becomes this is B. This is B over mu zero. Sometimes you write D here and multiply mu zero here, and multiply mu zero here, and D is epsilon zero times E. See, and then you have becomes an epsilon zero times mu zero, which is 1 over c squared. This is the microscopic Ampere's law. Okay, so so we can do that. We can now again you have J, you can just substitute J into here. For rho, you can use the charge density. You can use the Gauss law. Divergence E now is for microscopic is rho over mu zero, epsilon zero, right? So now you can substitute rho as epsilon zero times divergence E. Epsilon zero E and then divergence E. Good. So that's this term, and then this one is J is now 1 over mu zero curl B, right? And you divide by mu zero. This is mu zero epsilon zero. So that becomes epsilon zero. We could actually just let it cos B first, and then the other term is the same. But you move it to the other side. So minus. You have just epsilon zero, and then partial E partial T. E partial T cos B, and then finally everything integrate over the volume. Okay. So that is that, and I mean the derivation is kind of complicated, a little complicated, but the goal is to write down something similar. Like remember we work on the conservation energy. We want the total derivative, so like divergence of S. Now this is a vector. We'll basically get its total derivative of now instead of a vector would be a tensor. So that is the goal. You can say it's a divergence instead of divergence of vector divergence S. We have a divergence of a tensor, right? So and then plus something is a total time derivative. So now you have a time derivative of T, but it's not a total time derivative yet. So you have just E and then cos into B. Okay. The one thing you can do is using the curl of no, this seems to be fine. We'll work on that later. The other term is you need partial B, partial T, and now that you need the curl E. Where is the curl E? Let's see. Now the equation is the equation below 6.115. I think we are just using this, just take the time derivative on E cos B, total time derivative, and then you subtract it, the extra term. Let's keep writing. Then that is magnetic term, cos B. And this term becomes also T. We want the total time derivative. But then this one will give you difference, this one plus another term, so you need to subtract that, but this is minus sign, so you actually add option 0, B cos also B partial T. Now you can use the Faraday's law. Partial B partial T is minus of curl E. So you have E cos curl E, but in the minus sign, right? But you also change the order of E cos curl E become curl E cos E, and put it back to the positive sign. All together, you have your epsilon 0 divergence E plus curl E cos E. That's the electric field term. And then for magnetic field, you have this one. You have something similar to here. You have curl B cos B, but to make that the same as this one, we can add a divergence B terms, because divergence B is always 0. Basically, you just add in a 0 term. So basically, the second term is, because then one of them is 0. You have B divergence B and plus curl B cos B. Okay. So that will make it the two terms basically the same, formally the same, right? Because they are just different vector, but of the same kind of operation. Okay, and finally is this total derivative. That means this is just epsilon c, right? Let's just look at the first. Yeah. I think it's the same. Now this is the total time derivative. You can again take the time derivative out of the integral and just integrate that. Integrate epsilon 0 e cos b, right? And then the idea is that that would be interpreted as just like this is mechanical momentum. That would be interpreted as the time of change of the field momentum. This is a negative sign. You can move that to the left-hand side, become plus ddt of epsilon 0 e cos b, and integrate over space, and that will be interpreted as field energy that is 6,117. So, you can do. This one? That cross for the E electric field. For the electric field, this one? This one is from the Faraday's law. So partial B, partial T change the minus curl of E. Right? That one, and then there's a negative sign, you change it back to curl E cos E, that become positive signs. Okay, and now we just talk about this the interpretation, and you define now the P momentum of field is defined as this integral of this epsilon 0 e cos b. You know that e cos b is similar to what we learned in the conservation of energy. So that is kind of close to Ponting. For Ponting is like e cos h. E cos h is b over mu 0 for vacuum. You multiply by mu 0. And the combination is 1 over c squared. That is e cos h. Okay, and that is S. This is S. We integrate, now it's a volume integration of the S, and we divide it by c squared. That would be your field momentum. And likewise, you can define the momentum density. Momentum density is whatever in the integral. So momentum density is field momentum density is e cos h over c squared or S over c squared. This S over c squared is field momentum density. Okay, with that, let's move to the other side. You can now interpret that as conservation of momentum. But the rest is to write these two terms in the total derivative, and it would be total derivative of a tensor. Okay, and or integration of a tensor. Okay, so now we continue. Okay, this is the definition. Let's get some space to work on this. This is a little complicated. Hopefully, we still have time. So we can work on either one of them, and because both are the same, so once you work on one of them, the other is just the same. So I mean, there's two different ways to work on that. What Jackson did is using this, just consider one component, and then once you get work on one component, and then it's clear to see that the other components are the same, then you can combine those as what the final form you want. Another way to do it is use what we call the tensor notation. So if like you can work on like ijk as your unit vector, or so this will be the I. So divergence is just total. I mean, this is after you do a derivative, so there's no second index. So index will be sum over the index derivative and the components of E. So E, so it's like EI component, and then you have partial X, XJ, EJ, and sometimes we simplify just because we need to work on a few lines. So we sum over. This is the derivative over the X of J spatial vector, and this will be E sub J. Okay, so that becomes this one. Okay. Now this one is you need to do. I think I showed you something like that in last semester. So you have a cross product between this and that. So basically, it will be epsilon I j k of the j component of this one and k components of this one. So you will have an ek, and then the j component of this one. But j, this is also a cost, like a cost product, but it's a derivative cost. This is a curl. So this is a j component. So epsilon j I G K L M, and partial L EM. Right. Okay. This is that that's one will give you the J component of curl E. Okay. And then finally, yep. Okay. Now, what we can do is to simplify this because you have two epsilon. If we talked about that before, if you have two epsilon, you can change that to the product of quantical delta. Actually, there will be two terms, right? Remember I talked about this? Yeah. So, and then I also said that I usually like to put the same index, same index on the first index. So, like, if you cycle through this epsilon ijk, then the sign doesn't change. So ijk, you can move it to jki. So that won't change it. Okay. And actually, I don't want to bracket over here because I want to bracket this. The derivative only work on e sub m, not e sub k. And then this guy is using a formula is delta KL delta IM minus delta, just changing the L and M, interchange L and KL delta IM. So that is just the formula. And then now we can simplify. This is EI also J into J. And then the second term is this one, operate on this one. So wherever you see K, L become K, you have also K, and M becomes I. Okay. And then the second term is the other way around. L becomes I, and M will become K. And then you have K. Okay. Now we can see if we can simplify all these things. Now this one, obviously, you can simplify it. This is just because you have some repeated index is sum over it, but this is just like partial I ek 1/2 of ek, which is just the magnitude of E, right? Because we have this operator, just one of them. You put it inside the derivative. This is because you get this 1/2 factor because you are taking twice the derivative, and the two of them divided by 1/2 to get back to this one. Right. Now, the rest of this is let's see what the final form we want to get is. You have one of the. Basically, it's like first of all, because K and J dummy variable. You sum over them. This is ij. This is k ki. You can call k as j. Doesn't matter. You define your index, the name of the index. Right. Now, see, we can simplify that like integration by parts. So you have partial j, e, I, e, j. Okay, so the first term you take the derivative over this one, and then this another term is take the derivative of this one. So you need to subtract partial j, e, I, and then e, j, and then finally add partial j, e, I, e, j. I add back this term. But now you see that these two terms are the same. You just this is negative sign. This two term cancel. And this is still minus. There's a minus sign here. Okay. And now if you want to combine that, you can change that to let me write it. So partial j, e, I, e, j, and minus this combined with e square, just e square over 2. So e square over 2. But you want to do something like it's like the form here, so your partial j, but and then this is like a tensor. Now this tensor is simply the conjugate delta ij. You basically add the delta ij, but because this is partial j, if the delta ij becomes partial I, it's just the same as this one. Okay, but now it's both are in the same form, so you can combine them. Partial j, ei, ej minus e squared over 2 delta ij. Now this becomes a derivative of a tensor, right? And so partial j of this second rank tensor, this is eiej, and this is a delta ij. Okay. Now that is part of it. All right. That is this one. You multiply epsilon 0. And the same thing will apply to this one. Okay. It's just whatever you see, E, you change to B with this one. And then you do this one multiplied by epsilon 0, this one divided by mu 0. Now we can write down the conservation momentum. So you have ddt of P mechanical and plus the ddt of this one. Would we interpret that already as field energy? So you have epsilon 0 integrating E cos B into X. Okay, so that's the total momentum equals to, so you have partial J, everything has a partial J. Right, the first one is epsilon 0 multiplied by EI J. And then you have, or you can combine this one, but you have the same thing in B also. If you also pull out the epsilon 0 divided by epsilon 0, that becomes C squared. C squared EI EJ. And then the second term is minus 1/2 of epsilon 0 E squared Yes. No, epsilon zero is out. Epsilon zero out. E squared plus c squared b squared. Just like that. And then delta RT. Okay. And this is still in index notation. If you don't want an index notation, you can do vector vector notation also, except that the vector notation is might be a little bit not familiar. Basically, this becomes a tensor, right? This becomes and some people will do it EI. Just put the E to E together to represent this one. So this is E times E in the vector terms, not E dot E, this is E. This becomes C squared B, right? And this becomes what we call the identity matrix or identity tensor. So basically I, second rank identity matrix. And this one is, now you need to say that this is a divergence. This looks like a divergence, but the divergence means you are summing over the second index rather than the first index, because the result will be the vector in the first index. Okay, if you like, you can write down as a tensor. I mean the vector notation instead of using index notation. But sometimes in this situation, index notation is clearer, so it removes the ambiguity that this divergence is operate on the first index or the second index. So sometimes you need to define that. Otherwise, this divergence is not clear what this sum over. Divergence is sum over the partial derivative with component, right? But which component you sum over? Careful. But so if you use index notation, this would be the form. And I think Jackson used index notation also. And if you use the index notation, whatever inside this one, this whole thing is called defined as T ij. I think Jackson used alpha beta, doesn't matter. T, and that is called the Maxwell tensor or Maxwell stress tensor. Okay, this is a Maxwell stress tensor. And again, this is after the integration. This is the macroscopic form, right? And another step, because it's a total divergence, the right hand side you can forget about it. The right hand side can be changed to a surface integral as before. This is a total divergence of the index, so you can say it's surface integral of now is instead of T divergence of Tij becomes Tij, and then that in the normal is in the J components, is Nj. And N is the unit vector, but in the J component. Okay, and like that over surface S. So that would be 6112, 6 plus 6122, right? And this Tij is just this guy. Over here. All right. So that now the interpretation is the left-hand side is a total momentum, change of momentum, and the right-hand side should be the force. I think there's a negative. Oh, no, there's no negative. The negative sign is in here, but the T is defined as without the negative sign. So this T is the force acting on the system, on the volume. So if it's a positive, it means you give momentum to, let's say, like again, the pictures, you have the volume, you have the P mechanical. After you do the integration, you have P field. do this integral of the E cos B, right? And this surface integral is over this S. So the after you do the integral, this surface will give you either the momentum inside or outside. If it's positive, then will give momentum to the particle and field. If it is negative, we take the momentum, right? And so this the integral after you do the integral force, because a change of momentum is force. So you have so each area will give you a df, right? And so this dA is after for a little area, this Tij times Nj times dA will give you this df, right? And it has a direction because this is sum over j is and so therefore they interpret that as a stress tensor. It's similar to mechanical, how you define a stress mechanical system. Right? So therefore you call a stress tensor. Okay. Out of time, about time. Yeah, out of time. But that's a total derivation. It's a little long, especially how you make the form of a total derivative to get to what we call the stress tensor. But the physics is simply the conservation of momentum. Okay. Yeah. And any part you have questions?